Hello, I'm Dr. N.B. Hulle. In this video, we will try to understand analysis of transient response of RL circuit, that is, the first order systems. Here, I will divide this analysis into the three parts. One is source driven with zero initial condition. Second one is the source free, and third is source driven with some finite initial conditions. First, we will start with the source driven with zero initial conditions, that is the transient response of RL series circuit. Now here in this case, for analysis of transient response of the first order system, that is RL series circuit, we have considered this circuit. Here is the switch which is closed at t is equal to 0. Initially, the switch is open and the steady state was reached. And here it is RL circuit and we are applying the voltage, that is V, which is the DC voltage. Here, always while doing the transient response of any system, maybe the first order or maybe the second order, we will divide the analysis into the two parts. First, circuit analysis for t less than 0, that is before switching. And while using the analysis before switching, we will use the final condition of the network, because initially before switching the switch was open and the steady state was reached. And then we will take the analysis of the circuit for t greater than 0, and in which we will try to find out the expression. Now here in this case, we will do the circuit analysis for t less than 0. For t less than 0, the switch was in open condition. The R is the same as R, because initial condition and final condition of the resistance is same as we discussed in the previous video. And this inductor acts as a short circuit for final condition of the network, because before switching the circuit was in the steady state, that is in the final condition. That's why it was replaced by the short circuit and remaining circuit is the same. And through this we will try to find out what is the initial current or current before switching. Now here current at the time of switching, that is IF0 minus, is always same as IF0 plus, and which is equal to 0 from this case. Here in this case, whenever we have the energy storing elements, the energy stored before switching and after switching, or current in the circuit, especially in this case before switching, is very same as the after switching. That is IF0 minus is very same as IF0 plus, and for this particular case its value is 0. That is the analysis of the circuit for t less than 0. Now here I will come to the next part of the analysis, which is circuit analysis for t greater than 0. And we are interested in this part, and this part is known as the transient response of the system. In this case, this RL circuit is the first order system. That's why we are trying to analyze the transient response of the first order system. Now first we will apply the KVL to this case. Now here, if we are assuming the current as a clockwise, in that case this acts as a positive terminal of the positive terminal for this potential. This is negative, this is positive, and this is the negative. If we are applying the KVL here, and if we are traveling in the clockwise direction, for this particular case we are moving in the clockwise direction, means we are traveling from negative to positive, which is a plus. Its value of the voltage is V. Here we are traveling in the clockwise direction, that is positive to negative, it is minus. Voltage across this element is I of t into R, because I of t is the current flowing through the circuit. Then positive to negative, which is minus, voltage developed across inductor is given by expression L into di by dt, and after that there is no element in the circuit which is equal to 0, and this will be our equation number 1. Now here we will readjust the terms in the equation and we will find out its integration, and finally we are able to find out the expression for the current flowing through the circuit for t greater than 0, means we are able to find out the transient response of the system as far as the current is concerned. And then we will find out the voltage developed across inductor, maybe voltage developed across resistor, and so on. Now here in this case, rearranging the terms, what we are doing, we are shifting these two terms on the next side. Then it will be equation, we will divide it by the L, R, and it will be L by R, and I of t, it is V by R. Now here in this particular case, to simplify this analysis, we will use this V by R as a IM, that is maximum. As and when required, we can do the resubstitutions. Now here in this case, if we are expressing that equation, that is L by R di by dt plus it is IFT into Im. We are separating the terms, and if we are separating the terms, then L by R IFT we are shifting on the next side, and then we are using the variable separable method for the integration. And if we are integrating this equation on both sides, integration on the left hand side and integration on the right hand side. Now here we will multiply by the negative sign on both sides, because for this part of the integration, if the differentiation of the denominator is available in the numerator, then log of denominator will be the differentiation of or integration of this particular term, and its differentiation of this Im minus IFT, because Im is the constant, and differentiation of IFT with respect to t in this particular case is the -1. That's why we are multiplying by the -1. So we should have the integration or differentiation of that particular term in the numerator. Now here in this particular case, is differentiation is available in the numerator. That's why log of denominator will be its integration, and integration of this term R by L is a constant, that is minus R by L, and integration of this particular term is t plus some constant of integration. And here we will find out the value of this integration constant from the initial condition of the network, and we will name this equation as equation number 2. Now here, if we are putting the initial conditions, what we have the initial conditions, as already we have analyzed the circuit for t less than 0. At t is equal to 0, I have 0 minus is equal to 0 of I have 0 plus is equal to 0. If we are putting that value in the equation number 2, that will become log of, it is Im minus this term will be 0 plus which is equal to this term will be 0, which is equal to k, and we will get the value of the integration constant as it is log of Im. This log is nothing but it is natural logarithm, that is log to the base e. And if we are substituting the equation number 3 in equation number 2, we will get this final expression, that is log of Im minus IFT, which is equal to minus R by L into t, plus it is this constant k, and its value is, it is log of Im. And now here we will shift this log of Im term on the left hand side, then it will be the log of A minus log of B, means it is log of this term minus log of this Im, which is equal to minus R by L into T, and we will use the formula, that is log of A minus log B, that is log A upon B, means here it is log of Im minus IFT upon Im, which is equal to minus R by L into T. Now we will take the antilog on both sides. On this particular side, Im minus IFT divided by Im, which is equal to e raised to power of, it is minus t into L divided by R. I am adjusting these terms because as we are already aware of time constant, that is tau, for RL series circuit is nothing but L upon R. Means I wish to express this value or L upon R, or ratio of R by L and L by R in terms of the tau. That's why tau is L upon R. That's why I'm readjusting that particular value. Now here in this particular case, but we know that the time constant of the RL series circuit is given by expression L upon R, means it is Im minus IFT upon Im is equal to e raised to power of minus t by tau. And if we are simplifying this expression, that is Im minus IFT, this Im can be shifted on the next side, then this will be the expression. And finally, this IFT is equal to Im minus Im into e raised to power of minus t by tau. It can be expressed as it is Im in bracket 1 minus e raised to power of minus t by tau, and this Im can be represented as V upon R, in bracket it is 1 minus e raised to power of minus t by tau, and this is the final expression for the transient response of the current flowing through the RL series circuit. Now here in this particular case, this is the case in which we have taken the initial condition as 0, because current flowing through the circuit before switching, or current in the inductor before switching was the 0. Similarly, the voltage developed across inductor and voltage developed across resistor during the same case, we can find out those expressions also. But I always recommend, in place of using these formulas directly, use this basic version of the equation, because always the voltage developed across inductor is given by the formula L into di by dt, and voltage developed across resistor is always given by the formula it is R into IFT. By using the same equation, because IFT already we have prepared its equation, which is nothing but it is Im minus Im into e raised power of minus t by tau. We can put that particular value of IFT and we can differentiate that equation. Then we are able to find out the expression for the voltage developed across inductor. Now here in this case we will see how it is. Differentiation of this Im is a constant term and which is 0. Now this minus sign, it is as it is, and differentiation of e raised power of minus t by tau, it is minus 1 upon tau is the constant, then Im into e raised power of minus t by tau. And if we are substituting the value of this tau as L upon R, this L, and it is 1 upon L upon R into Im into e raised power of minus t by tau. Readjusting this term, this L will cancel with this value of L, and this is R into Im. This is Im into R, and this term is e raised power of minus t by tau. If I'm taking this whole term, that is Im into R can be expressed as its voltage or maximum voltage or applied voltage. In that particular case, the voltage across inductor will be V into e raised power of minus t by tau. That is the expression for the voltage developed across inductor. This is plus V into e raised power of minus t by tau. Similarly, the voltage developed across resistance is given by the formula that is R into IFT. That is, voltage across resistor is R is the constant term, IFT is nothing but Im minus Im into e raised power of minus t by tau. Here if we are multiplying by this R, that R into Im minus R into Im into e raised power of minus t by tau, this value can be replaced as a V. This can be V, means it is same as V minus V into e raised power of minus t by tau. Otherwise it can be expressed as, this can be expressed as V in bracket 1 minus e raised to power of minus t by tau. It is minus t by tau will be the expression for the voltage developed across resistance for this particular case. That is, voltage developed across resistance for this particular case. This will be the expression. Similarly, in the coming videos, we will try to solve the problems based on this source driven, source free, and whenever we have the initial condition 0 and we have some finite initial conditions, we will discuss those things. Thank you for watching this particular video. Thanks a lot.